Hi Anie.
Hi Janakiraman.
Hi Boby.
Hi Boby.
So welcome back. I think we are reconvening after all three of us after the end of this course on electronic systems, thinking and circuits. So the idea was to sort of give a students a summary of what we did in this course and also let them know what lies ahead for them in terms of what other courses they're going to do and how it is related to what we did in electronic systems thinking and circuits course. So that's the agenda for the discussion today. What did we do in this course and what lies ahead. Okay, so by now students would have figured out that a general electronic system typically has three major components. One is to sense, right? Like the microphone experiment that we did. You sense some data from the voice, it gets converted to an electrical signal. You then process it either as an analog signal or you can even take it into a digital computer and process that digitally, right? And eventually you want to communicate, we did amplitude modulation, frequency modulation, and then even looked at sending that data out through an antenna, right? So these are the primary building blocks of any electronic system. And in this course, we sort of went through, various aspects of these blocks essentially, right? So what did we do? We basically conducted and explained various experiments, right? So what were the experiments? We started off with dismantling a mobile, right? Looking at the miniaturization of electronics, how sophisticated packaging is today, right? Yes. In fact, it's very hard to dismantle, the mobiles that come out today, right? I did an iPhone 5s, which came long back.
Yes.
Okay, we also studied the battery in great detail, and that sort of led us into the concept of voltage, current. We also looked at the charger where automatically we got a feel for power, right? The battery gave us an insight into energy, right? And we also looked at a kettle, right? The resistance, Ohm's law and stuff. So effectively through these three experiments, we jumped into the heart of circuit theory. You both, I know, did a lot of KCL, KVL, superposition and so many things, right? Then after that, we went to a microphone. We did the sensing part, right? We said, how does a microphone sense? How it comes out as a voltage? It comes out with a DC offset with some wiggling voltage around it. We studied what a frequency means there, right? What a sinusoid is, right? And after that, we said, and we also did a lot of computational experiments there, right? You could amplify the voice, you could mix the voice, you could do so many things. We did all that. And then we, of course, went into the digital world, right? Because no computing today happens without some digital component to it. So we jumped into the digital world. We did a tear down of a laptop, right? And we discussed all the components. We didn't go too much into the digital domain as such, right? But we at least went from the analog domain using an ADC into the digital domain, right? So time sampling, time quantization and amplitude quantization. These are the two fundamental things needed to digitize, and that we discussed in great detail.
Yes.
Right? And of course, sinusoid filtering we have done in quite a bit of detail, I should say. Right, and this also is getting reinforced in the lab component of this course.
That's right.
Right, so I think this is something that should simply stay in the student's mind, right? And yes, and eventually we went and analyzed the idea of transmitting something on a channel.
So that's the communication part.
The communication part, either wired or wireless, and the need for modulation, right? Why we multiplied with a sine omega CT, the carrier frequency, and we also related it to the radio.
That's right.
Right, because it was very commonly used. So essentially, these are the I would say a subset of experiments. Right, we did a few more experiments as well, but effectively we sort of went through almost all of electronics with some first order analysis. That was the idea of this course. So the theory that we did, right, and the learning objectives of this course were entirely restricted to time domain analysis.
Yeah.
What can you do in time domain? And surprisingly, we did quite a bit, right? I think that is something that we learned
Yes.
through this course here, right? However, it is not sufficient to just stick to time domain analysis. It's okay for first order analysis, right? So when you reverse engineer something, there's a filter. We can represent that filter with a first order circuit and analyze it. But if you were to design that circuit from scratch, then you need a lot more than first order analysis, and your time domain is not going to help you in that respect, right? So therefore, future courses are going to allow more elegant and convenient analysis of systems to greater orders, right? So higher second order, third order, you can add as many capacitors, resistors, and still you'll be able to analyze it in a tractable manner, right? That's the idea.
Absolutely.
So question now is, what are these courses? Okay. So again, it's hard to say that every experiment that we did is actually corresponds to just one course.
Yes.
It could involve multiple courses, and all of that is needed to understand get a wholesome picture of the electronics that's actually going on. So for a start, maybe we can talk about, the battery, the charger, the Ohm's law, right? KCL, KVL. This leads us to the circuit theory, and I believe we have a course called Electrical and Electronic Circuits. So maybe the two of you can just give the students an overview of the course.
Sure. Maybe shall I handle that, Bobby?
Please.
Yes. So the follow-up course to this, one of the follow-up courses to this electronic systems thinking course is this electrical and electronic circuits, where we will take the paths where we analyze voltages, currents in the time and frequency domain ahead. So some of the things that we will learn is, for example, we have primarily concentrated on circuits with voltage sources, resistors, and capacitors. We will maybe start with learning a little bit more about inductors, inductive circuits, and some current source circuits as well. And we'll move on. So in this course, for example, in the present course, we only learnt about systems where you have components where you have one voltage and one current. However, the next level of abstraction is where what are called two-port circuits. So you basically have two voltages and two currents, and you have a very complicated network inside, but you abstract it out and say you only have a pair of voltages and currents, and how do you abstract out these kinds of circuits. And then we will then learn a little bit more about the frequency domain, because as you just mentioned, it's a very powerful technique, and it's really important for modern circuit design and system design. So we will learn that in a lot more detail and from first principles, right? And finally, we will take this to electronic circuits, true electronic circuits, because resistors, capacitors, inductors, they are all electrical circuits. But after all, this stream is an BS in electronic systems. So learning electronics is very important as early as possible. And electronic circuits are built with different kinds. They use resistors, capacitors, inductors, but you also need several new kinds of devices that are completely unlike these electrical circuits, and we will learn more about them. I'm sure students have learned or heard of components such as diodes, transistors, and maybe they've heard of MOSFETs and BJTs. They might have heard of it, but they will learn more about this. They are basically the building blocks of any electronic system, whether it's analog or digital. So they will need to learn to look at circuits that are built using these. We will look at very elementary electronic circuits, and then future courses will go on from there.
Okay. And these components, these transistors, they are basically what reside in these ICs.
They reside in these ICs. You may remember in electronic systems thinking, very early on when you took apart the phone and the laptop and so on, you talked about billions of transistors being
Correct.
packed into one single IC.
Yes.
So we are going to look at that building block.
That building
one
block,
transistor.
exactly. And I guess these, smaller components are also packaged in ICs, which they will be doing experiments with
Absolutely.
as part of the lab.
That's right. So we should maybe once you describe the other course as well, we'll talk about the lab.
Exactly. We'll
lab
talk
aspect.
about the lab aspect that together. Yes. Okay. Thanks for the introduction. Right. Now, we also did some audio signal analysis, right? We spoke about the terms like the frequency is, at most 8 kilohertz, and therefore you could sample at 44,100 hertz. These are standard numbers that we saw, but we didn't get into the details. We just said we gave a very intuitive understanding of sampling. As long as the signal is not varying too fast, it's okay to sample, slowly, kind of. That's the kind of intuition we gave. But there is very sound theory of exactly what frequency you must sample at in order to reconstruct that signal exactly, right? And all of that comes in your signals and systems, right? And you spoke about the frequency domain. Signals and systems probably is, I think that comes in the third right? Third term. And that, they will introduce frequency analysis a little bit here, but signals and systems will do it. It's sort of a vehicle that takes you from time to frequency domain.
Absolutely.
Right? Very formally, it's there are things like Fourier transform and Laplace transform that allow you to go in from one domain to the other, do analysis here, and maybe even come back to the time domain, right? And some aspects of this we have introduced in this course. For example, linearity.
That's
right. Homogeneity and all that, right? We did. So you'll study systems with, linear systems and see what you can do if you give an input signal. What will the output signal look like? If you know the response to a sinusoid, can you guess the response to any signal and stuff like that, right? So these are very critical aspects, and eventually, the course will end with some idea of sampling, right?
That's right.
If there's not enough time, sampling may be done in the follow-up course, which we will come to. But signals and systems, I would say, I think you will agree with me, is the foundation of electrical engineering.
Absolutely.
Right? You have to have the properties of Fourier transform, Laplace transform on fingertips, right? Because that appears, as you saw here, right? It appears across so many experiments that we have already done. So after that, we did this first order RC analysis, gave a step response, and then we did an experiment with the long wire where we had an overshoot, second order damping and then settling, right? So typically these things are done in a course like control systems, right? So maybe can you introduce the students to?
Yeah, so maybe sensing and control, because I think two courses are there.
Correct.
One focusing on the sensing aspect, other on the control aspect. If you take any engineering systems, for example, automotive system or even our cell phones.
Yeah.
I mean, just for example, if it's too bright, we can see that the display brightness is automatically adjusted. Yeah. So this has got some way to sense the brightness level outside, and then there is some way to adjust the brightness. There is some actuator adjusting that, and to do this, there will be some kind of control unit required. Somebody who knows, okay, this is what is required, and am I really reaching to that level?
Okay.
So that way, control and sensing go together.
Right.
This involves understanding of the sensors, understanding of the actuators, and at the same time, a lot of theory behind it.
Right.
The ways in which you can control, how to achieve the required error levels. Since you mentioned settling time, etc. Suppose if I want to settle in a given time, how will I reach that?
Right.
It involves, it's a combination of electronic systems and mathematics.
And mathematics. Okay. So, what you said seems to have some sort of an element of feedback.
Yes.
Right?
Yes.
So, because I think students would have heard these terms at least, feedback I think, maybe that, can you just tell the students about what to expect in terms of, when you're studying feedback, what are the kind of things that you might want to do and stuff like that?
Maybe we can take an example of this room temperature.
Okay.
So this room, for example, now is 24 degree.
Okay.
How is it maintained?
Okay.
So there are, sensors, temperature sensor that senses the temperature and gives maybe an analog voltage or a digital voltage to a unit.
Okay.
And then there is actively another unit making this room, cooler.
Okay.
Now these two will have to be, equal.
Yeah.
Correct. So you have some feedback going to your control unit saying this is my current temperature, and there is another unit trying to achieve that.
Okay.
So, even with, student feedback, correct?
Yeah.
I
right.
teach. Unless otherwise my students say,
Yeah.
I'm not able to follow this, or I'm, very clear about it.
Absolutely.
So
Absolutely.
so this is another way of feedback. So
Exactly.
I think there is nothing in this life without feedback.
Yeah. And I guess the other place where they would have encountered feedback is you take a mic very close to a speaker,
Yeah.
right?
Yes.
And it starts off,
Key
there's
sound,
a sinusoidal, high frequency tone
Correct,
that comes,
correct,
irritating tone. And that is sort of some positive feedback. So the system can also become unstable, I guess,
Yeah.
right? In that case. So control system sort of discusses some stability
Yes.
issues of
Yes.
a system
Yes.
as well, right?
Actually, these are found even in biological systems, right? So, your body controls its temperature. It is able to sense. You feel cold,
Yes.
right? Your body needs to
Absolutely.
produce more heat.
Yeah.
Your pupils of your eyes dilate and,
Correct.
contract based on amount of light going in.
Exactly.
So, actually, I would think feedback, especially negative feedback, is something fundamental
Correct.
to, practical systems.
Yes.
Practical systems, absolutely. So that's the significance of this control systems course. Okay, so moving on, so we looked at, digitizing a signal. We sort of take an analog signal, sample it, time quantize, and then we amplitude quantize, right? The amplitude quantized signal can then be converted to binary signal is what we discussed, and we just intuitively explained how to convert a decimal number to a binary. We didn't go into details. But this next course on digital systems will essentially tell you how to build the elementary components of a microprocessor, right? A microprocessor is what allows you to program and compute and do all sorts of things today, right? Right from C to Python to Java, there are just so many languages on which you can easily program complex stuff, right? So all of this is enabled by some digital logic gates which are sitting inside your microprocessor, right? So the idea behind digital systems is to just look at how you can logically manipulate signals, but more importantly, how you can arithmetically compute in a very consistent manner, right? We had briefly shown, for example, in this electronic systems thinking and circuit, whether you come from the analog, you compute in analog and feed a speaker or something directly, or you bring it into a digital computer, do some computation here and then feed it back. Barring the quantization error, it is still the same, right? So that is achieved with very rigorous mathematics of the number system, right? So we will start with the number system, we will build logic gates, we'll tell you what a logic gate should do, and eventually, after doing a digital systems course, the students must be able to build a control state machine. That's the end goal of that course, right?
Yes.
The microprocessor ultimately has a controller which is controlling, getting data from memory, getting something else from somewhere, performing a computation, sending it back. That kind of control system, right, is what we are going to look to build in this digital systems course.
Absolutely. So in fact, if I remember correctly, when I studied digital systems, you stop dealing with voltages and currents and start just dealing with numbers. There is a level of abstraction involved, right?
There is a very big level of abstraction. In fact, there are two things. One is the logical computation, where you are talking about true or false, right? And if you're talking about logical statements being cascaded, any true or false will work. I mean, you can call it true or false, 0, 1, -5, +5, it doesn't matter.
Yes.
But if you want arithmetic computations to be consistent, it has to be 0 and 1.
Yes.
Because
that's
the number system demands this. So
correct.
It's a coincidence that 0, 1 actually matches your true or false.
Yes.
And logically, these two are sort of coexisting. But the number system is deeper.
Is more
and
fundamental.
allows more fundamental and allows us to do computations correctly without any inconsistency. So absolutely.
Perfect. And I think they will complete the loop with connection of the digital systems to the voltages and currents and so on, maybe in a later course.
Yes.
Right.
In a later
so
course.
that still needs to be completed at some level.
Yes.
Because they are still electronics.
Correct.
Right. Electronic systems.
Absolutely.
So they will complete that
Absolutely.
in a later course.
Yeah.
Probably in the sensing course they will do.
They
Yes.
will do that. That is true.
Yeah. And also it's important to mention that, you just mentioned about this 8 billion transistors, right?
Yes.
8 billion transistors cannot be built from logic gates.
That's right.
So you need a higher level of abstraction which comes in this digital design course, which comes later.
That's right.
But digital systems is the basic course. Unless you understand digital systems, you cannot do high level coding in very long.
That's right.
That's why the courses have been sequenced in that particular manner. After digital design, you can hope to generate something which has 8 billion transistors. And just to mention again, there is, like I said, right, the same experiment can involve many subjects. We did, the amplitude quantization and then got it into a digital computer. But time quantization, right, is what leads us to digital signal processing. Right. So maybe can you just talk about?
Sure. I'll just say a few words about this. So the idea is in signals and systems, you do everything in the time domain. Yeah. So you're dealing with continuous signals.
Yeah.
But we have seen the initial, glimpses of sampling and quantization in this electronic systems thinking course. And we'll see more of it in signals and systems. This digital signal processing course, or DSP, deals with what you do after you have finished sampling and quantization. So a lot of it will actually be, again, just like digital systems abstracted out voltages and currents into numbers, ones and zeros, you will do the same thing in DSP. So you will now deal with numbers and sequences and series of numbers and how you process them. And you will correlate whatever you do to those numbers to what you do in the time domain to continuous time signals as well. So you have the concept of digital filters, just like we filtered out sinusoids. Yeah. You have the concept of digital filtering.
Right.
You have the concept of digital amplification. Okay. And concepts like that. So you at some level, you also deviate into whether you're dealing with stored numbers in computers, for example, or you have to perform operations as and when they come. Yeah. So for example, you imagine that we are, look at the audio system, right? You can either record the audio and then manipulate it and then broadcast it at any time that you want. You may play it out or broadcast it at a future time. So that is one example. So you have a lot of time delay, you can perform a lot of computation. But now imagine that, I'm teaching a live class, right? And the students are maybe in a different building. Now that needs to be real time. There is very little time for me to perform a lot of computation. It still needs to be digitized and then communicated and then, but there are limited number of operations I can do and it is called real time. Yeah. So this course will teach both aspects of it as well. Okay. And the mathematics and the kind of operations that you do are slightly different.
Right. Okay. So I guess there'll be this counterpart of the Fourier transform as
absolutely. There is a discrete time Fourier transform and and so on. Absolutely.
Right? Okay. Excellent. Again, transmitting a signal. We had spoken about amplitude modulation. Usually, a lot of this is done in a communication course, which relies on frequency domain analysis, which is again taught in signals and systems, right? But in this course, we were able to convey the crux with just trigonometry. We just left it at that. But once you move to the frequency domain, you can do many more complex things again.
Absolutely, yeah.
Right? So finally, when you want to transmit a signal, you have to go like you mentioned during the discussion, an electrical signal is converted to an electromagnetic wave and it is radiated out of the antenna, right? So fields and transmission lines, electromagnetic fields and transmission lines are basically wired medium and wireless communication, right?
That's right.
So you want to just tell the students about
Maybe one aspect of it.
Yeah.
Basically, we have learned several building blocks, and when you make system, these building blocks may be in a one unit. I mean, they may start interacting.
Okay.
As you said, conductively
Okay.
or wirelessly.
Wirelessly.
So, how do you design systems and ensure that this finally leads to what you actually wanted to get?
Okay.
So, interference, how to handle noise. So,
Okay.
how to do the design, reaching these or reaching these specifications that we set.
Okay.
So, that will be one of the aspects of this course.
Okay. So you're saying that the moment you have current flowing in some loop here, you can have a magnetic field that is
Yes.
remotely affecting a circuit nearby,
Yes.
right? And imagine 8 billion transistors in area of
Yeah,
25 mm by 25 mm, right?
Absolutely. Yes.
Then you're talking of
correct.
very close circuits, right? So
Absolutely.
even the 1 by r square effect is not going to be there. You're going
Yeah,
to have
yeah,
a serious interference. So that is what we are going to cover in this course. And what are these transmission lines?
Okay. So I'll connect it to something that you just said.
Yeah.
8 billion transistors.
Yeah.
Right. So you imagine you need to send us digital signal
Yeah.
from one end of the IC to another of your microprocessor.
Okay.
It needs to be sent along a wired connection.
Yeah.
And now at these, if you see modern, computers, they're all running at gigahertz speeds.
Yeah.
So which means the time period is just a few, maybe hundreds of picoseconds
Yeah.
to maximum a few nanoseconds.
Correct.
Which means the wavelengths are actually extremely small. So even a millimeter across one end of the IC to another can actually lead to delays. And these delays matter in processing signals.
Yeah.
Now you can go to the next level, which is now I'm imagining maybe one IC talking to another, maybe a microprocessor talking to memory. That would also be technically a transmission line because the distance would be a few tens of millimeters or a millimeter to tens of millimeters between ICs. There are a lot of cases in electronic systems, analog or digital, where you would have this effect. Obviously, on the analog side, again, if you have high frequency circuits, maybe from one amplifier to another, if you have two different ICs, if you have a connection between them, that would act as a transmission line.
Okay, so essentially you're saying that what is supposed to be a simple short circuit between 2 points, is it?
Yes.
And this is what we saw in our course here with this big loop of wire.
That's right. We did an experiment, right?
We actually saw, we took the multimeter, saw that it was a short.
Yes.
But when we conducted experiments at higher frequencies, we saw ringing, we saw all sorts of things,
Yes.
right? So there are capacitances and resistances everywhere,
Yes.
right? Even if you want to avoid them, you can't.
In fact, the transmission lines portion starts with resistors, capacitors, inductors, and conductances. Yes.
Right?
So that's
Okay.
right.
And the effect of basically sending a signal. So how long the wire is actually depends on the frequency,
That's right.
essentially. Okay, so that is what we will look at in this particular course. So there are, a lot of advanced courses, I guess, right? After this, what we spoke about are just the basic building blocks of electrical engineering, right? What we call the core courses.
Absolutely. Actually, what we have covered is only till 4th or 5th semester.
Yes.
They have almost half the, degree
Exactly.
to go after that.
Exactly. But I guess the point there is once you have done these basic courses, you can do any course after that because everything is built on those foundations. Like I guess analog circuits,
Yes.
for example, right? I mean, maybe you can just tell them the typical kind of things that they would experience there.
Absolutely. So in the next course, which is electrical and electronic circuits, you get a glimpse of the transistors and diodes and so on. Analog circuits takes it to the next level where you learn to build circuits using those components. And there is one level of abstraction as well because you have a component called an op-amp, which acts as a general purpose electronic element.
Yeah.
which just like you have resistors, capacitors and inductors, you can think of an op-amp as a general purpose building block for analog electronic circuits. So they'll be learning how to use that to build complicated circuits such as amplifiers. And Professor Boby talked about negative feedback and control. You will see aspects of that because any op-amp based amplifier, for example, has to have negative feedback. It needs to be stable. So they will be looking at aspects of that as well. Excellent. And one more thing I just wanted to say, you talked about core courses. Now, the reason each of these courses is a core course is because some aspect of these courses will somewhere or the other, you may specialize in digital circuits or systems, for example, but there'll be some aspect of, maybe transmission lines, like I said, interconnects.
Correct.
There may be some concept of, resistors and capacitors, RC circuits where you'll need to use. There will be some aspect of even analog circuits that maybe you need to, if you have a memory circuit, for example, you need a sense amplifier to make sure that you're able to read and write to memory.
Correct.
So there is some aspect of each of these courses that you need to build a working system in a specialized area as well. That is why these are core courses.
Yeah. So essentially, you're saying you can't ask ChatGPT to give you a sense amplifier and
Absolutely
then be done with it. Right?
Correct.
So basically, you need to have an understanding of all those components.
Absolutely.
Right? So I think this is sort of a very good overview of the courses, and we have gone from the core to the advanced. Beyond that, they can do electives.
Yeah.
Essentially, right? You choose your specialization and do courses of your interest, essentially, right? And of course, you also will have math courses sort of teaching you the fundamentals all through.
That's right. I think maths and then I would say the programming side of things as well.
Correct.
Right? That's an extremely important part of modern electronic systems. So broadly, I see the way we are seeing this, there seem to be maybe 3 streams. Right? There is an analog electrical circuits, electronic circuits, analog electronic circuits, sense amplifiers, that stream.
Yeah.
Then there is a digital systems, then digital system design, FPGAs, and that stream is there. And then there is a programming side, right? And the maths kind of forms the basis for all of these.
For all. Yes, absolutely. Okay. So I think we'll leave the students with this slide: sense, compute, communicate, and I think he mentioned actuate at some point. So
yes.
It could be an actuation also there. You are going to be studying this in great detail in the coming years. So hope you have a good time with the course. Good luck.
Good luck.